Hello all, welcome to VZD Academy. This is Anil Kumar, Faculty of Digital Electronics. Sir, up to now we have seen three types of basic gates: NOT gate, AND gate, OR gate. Now let us try to understand the new concept. We can say new gate called universal gates. We have two types of universal gates, which are NAND gate and NOR gate. We can also understand this NAND gate and NOR gate the way we have understand the way we learned OR gate, AND gate and NOR gate. Not gate, we can say. Sir, let me try to explain here universal gates. Basically we have two types of universal gates, we can say, which are NAND and NOR gates. Sir, let me take here the first gate called, we can say, the fourth gate. We can also tell that because we have learned three types of basic gates, which are AND gate, OR gate, NOT gate. Now let me explain the fourth gate called NAND gate. NAND gate. Sir, I told you in the previous lecture, even the moment when we learn about any logic gate, we just need to remember few things, which is first one is logic circuit, and second one is truth table, and third one is, we can say, logical expression, and fourth one we can say number of inputs and outputs, fifth one commutative law, and sixth one associative law, and seventh one enable input, zero condition, eighth one enable input, one condition. And also we just need to remember the last case, unused input case. These are the things which we need to remember. Sir, from fifth point onwards, very important, fifth, sixth, seventh, eighth, ninth, from the competitive exam point of view, we may get the questions based upon these last 5 points. Let us try to understand NAND gate. Here the first thing that we need to remember, what is the logic circuit. Sir, logic circuit of NAND gate is similar to AND gate. Here similar to AND gate, but only the difference is here this gate is also having two inputs A and B. And now if we can connect one NOT gate here, the output will become Y equal to A into B whole bar. Up to this, here we can take output as Y equal to A into B, as similar AND gate. When we connect one NOT gate here, the output will become Y equal to A into B whole bar. Sir, we can also draw the NAND gate like this. Here this is NAND gate. You can say we can put one bubble here, so that output will become Y A, and then this is B. Here Y equal to A into B whole bar. Sir, we can also write the logic circuit like this. Sir, the next thing, we have completed the first point. The next thing is truth table. Here truth table of NAND gate. We have two inputs here, which are A and B. So based upon inputs A and B, and now output Y equal to, we just need to take here A and B, and then the second case Y equal to A B whole bar. Let us try to understand the truth table like this. Here inputs 0 0 0 1 1 0 and then 1 1. 4 cases we have. Sir, now for these 4 cases, let me try to understand the truth table of NAND gate. The moment when I apply A equal to 0 and then B equal to 0, here A equal to 0, B equal to 0, what will happen? Sir, here 0 into 0 for this particular y equal to a into b condition up to this we can get, we can analyze multiplication operation. Of course, multiplication operation, 0 into 0 0, 0 into 1 0, 1 into 0 0, and then 1 into 1 1. Exactly complement of AND gate. So now here A into B output is this. Now when we make complement for this particular output y equal to A into B, automatically 0 will become, we can say 1, and then 1 1, finally 0. So this is what we can say the output of NAND gate, or we can say truth table of NAND gate. Sir, now let me take the third point. Here we have completed the second point. The third point is logical expression, y equal to, or we can say logical expression, sir. Here y equal to A into B whole bar. This is what SOP, sum of products form. We can also write this logical expression y equal to A bar plus B bar. This is called product of sum, POS, product of sum form. Let me explain what is SOP, how to convert SOP to POS, and then what is POS, how to convert POS to SOP when we dealing about Boolean algebra. Let us try to understand as of now. Y equal to A into B whole bar, SOP form, sum of products, and then y equal to A bar plus B bar, POS from, we can say product of sum. Now the fourth case here, we have fourth case, sir, number of inputs and outputs. Sir, based upon the logic circuit and then truth table and logical expression, we can say that we have only two inputs, which are A and then B. Here number of inputs, we can say 2, and then number of outputs, we can say 1. So this is what inputs and outputs. Let me take here the fifth condition, commutative. What is commutative? Let us try to understand. Here fifth condition, sir, I told you in the previous lecture even, the moment when we interchange the number of inputs, the available number of inputs, we can say when we interchange A to B and then B to A, if the output is same after interchanging the inputs A to B and then B to A, then we can say that the logic circuit is satisfying commutative law. Let us try to understand. This is what NAND gate, sir. This is NAND gate A and then B. Here y equal to A into B whole bar. We know that the truth table of NAND gate, here A, B, y equal to A into B whole bar. Here 0 0, 0 1, 1 0, 1 1 are the inputs, and we can say output will be 1 1 1 and then 0. This is what NAND gate truth table. Sir, what I am trying to tell here is, suppose if I can interchange, this is what case 1. Here we can say case 1. And now let me take here case 2. The moment when I interchange the available inputs, here this is B and now this is A. If I can interchange the values, this is NAND gate. Now let me take y equal to B into A bar. If I can interchange A to B and then B to A. If both the outputs are same, we can say that the circuit is satisfying commutative law. So here whatever the thing may be, here we can say here A equal to A into B bar equal to, we can say B into A bar. Based upon truth table, this condition is satisfying, so that the NAND logic gate is satisfying commutative law. Now let me take the sixth condition here. Sixth condition is associative law. Associative law. Here, sir, the moment when we add one more input to the here logic gate, we can say here NAND gate, which is having inputs A, B, and now here output is, we can say Y1, which is equal to A into B whole bar. And now let me take third input C. Here output Y1 and then third input C. when I connect these two inputs y1 and then C to another NAND gate, here output will become y2 equal to y1 into C whole bar. So this is the condition. Let me draw here y2 equal to y1 into C whole bar. Here I know that y1 means A into B whole bar into C whole bar. This is the equation of y2. This is the equation of y2. And now let me take here. Suppose if it is case 1. Let me take here case 2. Sir, the moment when I interchange here NAND gate, let me take here B and now this is C. Here I can say NAND gate with a bubble y1 equal to B into C whole bar. So this is what output y1. Let me take here input A and now A and then y1 I want to connect to another NAND gate called y2. Output we can say y2. Here y2 equal to we can say y1 into A whole bar. Sir, let me try here. y2 equal to y1 means B into C whole bar into we can say A total bar. So now if this y2 and this y2 is similar, we can say when we draw the truth table for these two logical expression, if truth table is similar, then we can say that the logic circuit NAND gate is also following associative law. But sir, here let us try to understand. Here y2 equal to A into B bar into C whole bar, which is not equal to B into C bar into A. So because these two expressions are not equal, when we draw a truth table or when we analyze or when we divide these logical expressions, because these two logical expressions are not equal, we can say that our NAND gate is not at all following associative. The leftover part here is enable input 0 and then enable input 1. Sir, let me take the seventh condition here. Seventh condition, enable input 0 condition. What is seventh condition? Sir, suppose this is NAND gate. This is NAND gate. If I can take here A, one of the input, and this is B. If I can apply B equal to 0 for different cases, even though if I can change A equal to 1 and then 0 and then X, let me take here some square wave, whatever it is. If I can change A inputs differently and then if I can keep on applying B equal to 0, what is the circuit behavior? Here Y equal to A into B bar. Sir, we know truth table A, B and then Y equal to A into B whole bar 0, 0, 0, 1, 1, 0, 1, 1 for the conditions 1, 1, 1, 0. This is called truth table. Now let us try to understand the behavior of enable input 0. Sir, the moment when I take here A equal to the first condition, here A equal to 1 and then A equal to 1 and then B equal to 0. What will happen? When A equal to 1, B equal to 0, we can say when A equal to 1, B equal to 0, output we can say 1. Here output is 1. And now the second condition, here this is what first condition, and second condition A equal to, here we can say A equal to 0 and then B again 0, which means we are applying B equal to keep on 0 for different conditions. This is called second condition. When A equal to 0, B equal to 0, output we can say again 1. Here also output is 1 again, which means this is second condition. Sir, let me take third condition. The moment when I take here A equal to X, instead of 1 and 0, I want to take some other element, we can say A equal to X and then B equal to, let me take 0. Here this is third case. What will happen when we take A equal to X? Sir, when this type of conditions comes, when examiner is asking based upon this type of conditions, when examiner is asking when input is X or something square wave or whatever it is, we just need to follow some logic here. When we look at the truth table, here when one of the inputs is 0, here output is automatically always 1 for the NAND gate. When one of the inputs is 0, here we are applying B equal to 0, keep on for different inputs of A. So the moment when I look into truth table, if one of the inputs is 0, we can say output is always 1, sir. Here B equal to 0, here one of the inputs is 0, output is 1. And then A equal to 0, though B is 1, we can say output is 1. Here B equal to 0, third case, though A is 1, we can say output is 1, which means if one of the inputs is 0, for the NAND gate case, we can say output is always 0. Here B equal to 0, even though A equal to 1 or 0 or X or whatever it is, we can expect the output is, without doubt any, we can say output is 1. And now let me take even fourth case also. Here A equal to, sir, square wave we have given here, and now square wave, and B equal to 0, we can say for the fourth case, we can say, sir, fourth case here B equal to 0, as I told you the logic, if one of the inputs is 0, output is automatically 1, though even if it is A equal to 1 or A equal to 0, A equal to X or A equal to square wave, whatever it is, if one of the inputs is 0, we can say output is automatically 1. So based upon the behavior of the circuit NAND gate, we can say it is producing, sir, for the four cases, it is producing the same output. We can say it is producing fixed output. Fixed output, we can say. So this is what enable input 0 condition. Let me take the 8th condition, sir. Here we have completed 7th case. Now let us try to understand 8th case, sir. Here 8th case 8th case enable input 1 case, sir. Now let us try to understand. The moment when I take this NAND gate, here A equal to, and then this is B equal to, I want to apply B as 1. Here A equal to, first of all 1 and then 0, and then let me take X, and then now this is square wave or something else. Sir, here Y equal to A into B whole bar. Let us try to understand. We know the truth table, sir. We know the truth table. The truth table of NAND gate is here A and then B, Y equal to A into B whole bar. 0, 0, 0, 1, 1, 0, 1, 1 conditions, we can say output is 111 and then 0. This is called NAND gate output. Now let us try to understand. When we apply A equal to 1 and then B equal to 1. Here let us try to understand, sir. The moment when I apply one of the inputs is 1, the logic is, if one of the inputs is 1, we can say output is complementing of another input. Let me tell again. Here when one of the inputs is 1, the output is complement of another input. We can say here the second case, sir. Here B is 1, which means another input is 0. So output must be complement of A. Because A is 0, the output is 1, complementing. And now here one of the inputs A is 1 and now B another input is 0. So that output is 1 because B equal to 0, now the output is complementing. Here B equal to 1 for the third case, another input A is 1. So A will become 0 because A equal to 1, this will be complementing, so output will be 0. So now based upon this logic, can I say that, sir, here B equal to 1 and then A equal to 1. We can say B equal to 1, A equal to 1. We can say output is 0. And now let me take the second condition. Here A equal to 0 and then B equal to 1. Here A equal to 0, B equal to 1. We can say second condition, sir, output is 1, we can say. And now for the third condition, here A equal to X and now B equal to 1. If one of the inputs is 1, we can say output is complement of the another input, which means here B equal to 1, we can say another input is X. So now output will become complement of another input, we can say X bar. And now the fourth one is A equal to square wave, we can say. Here this is square wave and now B equal to 1. So the moment when one of the inputs is 1, automatically the output will become complement of another input A, which means this is square wave. The square wave will be complemented so that output will be like this. Now based upon this analysis, sir, the circuit is acting as inverter here, because when we apply A equal to 0, the output is, when we apply A equal to 1, the output is 0. When we apply A equal to 0, the output is 1. When we apply A equal to x, the output is x bar. When we apply A equal to square wave, then the output will be reversed square wave. So based upon this, we can say the NAND gate, when we apply one of the inputs is 1, we can say the NAND gate is acting as a inverter. So this is what about enable input 1 condition. Sir, the leftover condition, we can say that unused input condition. Now let us try to understand unused input condition. Sir, unused input condition, let us try to understand. The 9th point, we can say unused input conditions. Sir, we have seen AND gate unused input conditions. The similar case here, we have 3 cases when we apply. This is NAND gate A and B. If we can take one of the third input, we can apply this third input to here, we can say 1. Suppose this is y equal to A into B whole bar. Suppose if it is TTL, transistor logic, we can say 1. And then if it is ECL, we can apply, this is 0 for case 1. Third input we can apply 1. Suppose if it is TTL logic family. Suppose if it is ECL logic family, we can take it as 0. And now case 2 here, sir, let us try to understand. This is NAND gate, and now A and B, the third input we can connect to here plus VCC, we can say collector controlled voltage, y equal to A into B whole bar. Even though if we can connect a third input to plus VCC, circuit can act as a NAND gate. And now third case, sir, here this is NAND gate, and now A and then B are the inputs. Suppose if I can connect third input here, available third input to one of the input, if I can connect to B, then even y equal to A into B bar, the circuit can work. If I can connect here A and then B, if I can connect the output to third input to input A, then also y equal to A into B whole bar. For this case also circuit can work. These are the possible connections for the NAND gate when we have unused input or floating input or extra input. We can connect to one, then the circuit works. We can connect the third input to VCC, then also circuit can work. We can connect third input to either one of the inputs, then also circuit can work as a NAND gate. So this is what about NAND gate, sir. Thanks for watching. Please do subscribe.